Hi, everyone, and thank you for joining us today. I'd like to welcome you. As usual, we always like to know where you're located, and thank you for being here. Jorge and myself, we're located in South Florida. So thank you, Raul. Welcome. Thank you. Peru's in the house, Jorge. So it's pretty nice. Cool. And we have some our
Nice.
friends from Georgetown, Canada, as well, are with us as well.
Hello.
Raul, really? Did Raul is saying that he actually had COVID? Oh my!
Wow.
I hope you're doing well, and hopefully the rest of the family staying safe as well. I wish you the best, Raul. And we have from Georgia. Hi, Jack. Thank you for being here. Greatly appreciate it. Thank you for joining us. Before we begin, does anybody have some experience using Fusion 360 electronics or possibly Eagle? I'd like to know. Are you currently using it, or you have any experience with it? Okay, so California. Thank you, Bob. Appreciate that, Bob. Actually, Bob Miller. Bob. I think Bob has been using Eagle for a while, if I'm not mistaken, right, Jorge? Does that you recognize that name? I'm pretty sure
The
Bob has been
Miller,
with us.
the Miller. My, I recognize the Miller. Maybe it's the same one that I
Okay, yeah, I
remember.
think.
But
Well, thank you, Bob. Thank you for being here. Appreciate that. Okay, okay, so we have some. Okay, we have some students using Eagle for their university projects as well. That's pretty neat. Cool,
cool.
love it.
Nice. So they'll feel right at home with Fusion 360 electronics.
Absolutely, yeah, they'll be right. And take advantage of those transparent electromechanical capabilities between the electronics and the mechanical side as well. Okay, we have some Francis. He's a Eagle veteran, that's for sure. He's been using Eagle for a little over 7 years already. So we have our veterans with us. As I said earlier,
Ed, you there? Ed? Ed?
testing 1 2 3, testing 1 2 3.
Yeah, I can hear you just fine.
Okay, just to let you know, due to the current a situation. So we're currently working from home. So Jorge is closer to Miami. I'm just north of Miami myself, further north. So the topic today is one that has been requested quite often from many users, and it's about routing. Routing is one of those features within the Fusion 360, which is quite elaborate. There's actually many tools of it. But instead of actually working with Fusion and teaching you more about Fusion and how to use it, we wanted to go over, and you'll be seeing more of this. We're going to go over more about actual circuit board and the electronics behind it and on the circuit boards itself. So Jorge came up with the idea of maybe we should cover all about high speed designs and 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 how do you take care or how do you handle traces or signals, I should say, signals which are going to be carrying high speed frequencies on them? How do you treat that? What are the special steps that need to be taken, or what are the effects that you need to be taking into consideration when you're doing some high speed routing? So today, Jorge is going to be giving us um, a review on that as well. And so my first question, and I guess it's my last question, Jorge. So exactly what constitutes a high speed signal? Could you tell us a little bit about that, please?
Yep. Let's go into it. You can hear me fine, right?
Yeah, you sound good, Jorge.
All right. So I'm going to stop that PowerPoint. Give me 1 second. Okay. There we go. And let's start this new one. Okay, let's see if I can share this one now. Okay, can you see it? You see it, Ed?
Yeah, it looks good.
Okay, excellent. So basically, this is meant to be an introductory webinar. So we're just going to start scratching the surface. This is a topic that we could easily do several webinars on, each several hours long. But the idea is that we do this one in 30 minutes. So keep that in mind. We're really, really limiting the scope. So the idea in this webinar is we're going to go over these basically 4 points. First is, when do we need to worry about high-speed routing? How do we know what it is? And when we can fall back to our normal circuit theory, and when do we have to deal with electromagnetics theory? Okay. After that, we're going to go into some basic guidelines and rules of thumb for high-speed routing. Then I'm going to share some resources, because really, to go in depth, you're going to need more than just this webinar. So I'm going to share some of the resources that we recommend. And then we're going to go through an example in Fusion 360 Electronics. Okay. So what constitutes a high-speed signal? Okay. The way you can determine whether your board has high-speed signals or not is looking at this image right here. Okay. So your signals have a length based on their frequency and how quickly they move through the board. Okay. So notice I have a little equation there in which wavelength is equal to the speed of light, which is c, divided by the square root of the relative permittivity times frequency. Now, lots of big words, but it simplifies. For an FR4 board, the traces on FR4, the relative permittivity is 4. Square root of 4 is 2. Okay? And then the rest of it we know as c, speed of light, and f, frequency. So at high frequencies, the higher this f is, the smaller the wavelength. Okay? So why is that important? Why is it important to know the wavelength? Well, what's going to happen is, when dealing with your circuits, okay, your traces have a certain length. If the length of your traces is much smaller than the wavelength, as you can see in this picture, then you can basically say that the signal is the same everywhere on the board. Okay, you don't have a variation in distance. So when you can do that, you can see that your traces are much smaller than the wavelength of the signals on your board. You can completely ignore this. You don't have to worry about any of this. All of your traces are transparent. What happens on one end of the trace instantaneously happens on the other one. Okay? And this is maybe where most of us are used to living in. Okay? Where the board and the frequency of the signals on your board is very small compared to the wavelength of those signals.
So in
So,
other words, usually the most common board that we working on for our like our hobbyist reasons are in that range then?
right. So stuff like the Arduino tends to fall in this range.
Okay. Raspberry Pi.
If you were using it in your projects, yes. If you were designing a Raspberry Pi from scratch, no. They have
Okay,
to
yeah,
worry
got
about
it,
this
got it. Yeah,
stuff.
of course, of course. Yeah, you bet, you bet. Got it.
They definitely have to worry about this
So like the
stuff.
shields and items of that nature would usually be regular
Right,
speed then. Okay, cool.
typically. So typical hobbyist stuff doesn't have to worry about high speed signals. Okay? Simply because if you notice, let's say for example, audio. The human audio range is from 20 to 20 kilohertz. Okay? So if you plug in the information, you plug those values into the equation, what you end up getting is something like, the wavelength of a 20 kilohertz signal is something like a few meters, a few tens of meters. So no PCB is that big. Hence, you can pretty much ignore worrying about any of this stuff. Now, if you're doing something like USB or Wi-Fi, Wi-Fi is typically 2.5 gigahertz. So in those situations, the wavelength is less than a few centimeters. So now you have a problem, because the traces on the PCB are more than likely going to be maybe a few inches, right? So if you think about it at those points, now this assumption doesn't hold.
Yeah, it's too long.
So that's basically what we're saying here. If the length of your traces is less than about 1/10 the wavelength, then you don't have to worry about it. And when you do the math and you translate it, you get this rule of thumb, which is just that. So if you're once you go into the nitty-gritty of your design, you do have to confirm that this is true. But as a rule of thumb, if you have things that are 100 megahertz or higher on your board, you're dealing with high-speed signals. Okay, so all of this math in a quick blink of an eye, you can just say rule of thumb 100 megahertz. Now, be careful. A rule of thumb gives you a quick answer, but not necessarily the most accurate answer. Really, it depends on the rise time of your signals, but that's something that goes beyond the scope of what we want to do today. But you can have a 10 hertz, a really slow signal, but if it has a very fast edge, then that fast edge causes it to be a high speed signal. Okay?
So rule of thumb, our threshold is 100.
100, right? If you have no other information, if you're not sure, if you see 100 megahertz or more, you have to start worrying about high speed.
Got it.
Okay?
Got it.
So few basic guidelines, and really this could be a much longer list, but just for what we're going to do today as our example, and spoiler alert, we're going to do a USB example today. Basic rules that you always want to keep in mind. Keep traces as short as possible. That minimizes all problems. The shorter you can keep the traces, the less you have to worry. Okay, so that's a general guideline. Whenever you're routing and you're working with your high-speed signals, the shorter you can keep them, the better off you'll be. Second rule of thumb is you want to try to use copper planes for your reference voltages. So what does that mean? Most of you are familiar that in a PCB, usually you'll have a ground plane on the bottom of the board. So if you have a 2-layer PCB, you'll try to get most of the routing done on one layer and then use the other one as a plane for ground. And this has several benefits. It gives you some shielding against electromagnetic interference. It also allows you to have good return paths typically, so you'll be able to have lower impedance to ground, avoids things kind of floating. And it also helps with manufacture. It keeps the board a bit more stable. So in general, there's no downside to using a copper plane. In Fusion Electronics, they're very easy to produce using the polygon command. So use them whenever possible. Okay.
Does it matter the layer, Jorge? Does it where you define your pores, your polygons?
So ideally you want a polygon to be on its own layer. If the board is not high speed, you can get away with it not being its own layer. In other words, having some routes through it. In the example we're going to go to today, it is really highly recommended that you have copper planes on their own layers. Okay, and that's something we're going to go into and how you can set that up in Fusion Electronics.
Cool.
Okay, the third basic guideline that we have here is to terminate nets to avoid reflections. So the idea here is when you're dealing with high-speed signals, impedance needs to be at the forefront of your mind. You want to make sure that the signal doesn't see changes in impedance. Whenever there's a change in impedance, you'll have some signal distortion. Okay? If the change is minor, then it might be okay. But now, if you have these large changes in impedance, what can happen is you can get so much distortion in the signal that you won't be able to extract it. You won't be able to read it when it gets to the other end of the line. So that's something that we'll actually show briefly today. Although in this particular application, it's kind of taken care of for us, but it's something to keep in mind. And then
What could affect that impedance? Could it be a bend that goes in a different direction, or
so that's a big
change width?
right. So change of width will affect impedance. Another one is a bend. Now there's been this long-standing kind of rule that when dealing with high speed, you avoid 90-degree angles, okay, at all costs, because at the corner, you actually the thickest part of that corner is actually 1.5 times your width, roughly. So there's always been this idea that you have to avoid that because it'll create a lot of distortion there. Well, when you start looking at the math and you work it out, a corner is only really important if 10 femtofarads of capacitance is important. Now, 10 femtofarads is basically a decimal point followed by 15 zeros and then a 1. Okay? So we're talking a really, really tiny amount. If that's important, then you have to worry about the 90-degree angles. If not, then, you don't really have to stress it. Out of convention and what most people are used to seeing, just stick to 45s. That'll help minimize it. Another thing that can help, or a situation where this can come up a lot, is when you have a voltage signal going into an op amp or some sort of driver. If you look at what's going on there, you'll have some impedance going into a very large one, because op amps in general have high input impedance. So in a situation like that, if you have a high-speed signal, you're going to get a lot of reflections. Okay, and that's why termination becomes important. But
Okay,
again,
cool.
that's something we can go in depth in a different webinar.
Okay, thank you, Jorge.
And then finally, we have this rule, which is going to be important for us today, which is to avoid all asymmetries in a differential pair. If you have differential pairs in your design, they take priority. You need to do everything you can to keep them identical. And if you can, keep them on the same layer. Any transitions are going to affect the impedance of the differential pair. So if possible, you really want to try to stick to keeping them all on the same layer.
So you don't want to be transitioning from the top to inner layer, bottom layer, and then coming back up or something like that. Just
Correct.
stay on the same layer. Okay.
Right. Again, if you can avoid it, it's not always avoidable, but in high-speed design, the high-speed signals take priority. So if you route them first, you can usually guarantee that they're not transitioning layers, usually.
So would you recommend then any signal that has high speed or that we need differential pair? Would it be recommendable then that we start with those traces, with those signals first?
Correct.
That way that way it's doesn't make it, they're not in the way of when we're doing the rest of the board. I'm suggesting, or if you want to use the auto route or something like that later on, at least get those done first.
Correct. Yeah, I mean, you can't, it's hard to generalize, because if a design, for example, has low-level analog signals, depending on where they are and what sensors you're connecting to them, those have to. But in general, this qualify as a critical trait and would be one of the first ones that you would route. So yes, we'll go with that.
Cool.
Okay. So resources for more information. Okay. Definitely, like I said, we're just going to scratch the surface in today's webinar. These are two app notes from Texas Instruments. They're both very good. I do recommend them for whenever you're dealing for high speed. But if you really want to understand high speed design in general, the book that I like is Signal and Power Integrity Simplified. This isn't a paid commercial. I have my copy here at home, but it really addresses the topic in a nice, approachable way. There is math. This is engineering. You can't get away from math, but is not as dense as some other text on the subject, and it really tries to build intuition on how things behave at high speed. So I really recommend this book. It's funny, the title Simplified is a little bit of an oxymoron, because the book is still about 500, let me see, it's a total of 700 pages long. So simplified is a relative term in this case, because the book is about 700 pages long, but very much worth it. So with that, let's go ahead and get to our example. So I'm going to go ahead and escape this. And I'm going to go ahead and share my Fusion screen. So give me 1 second.
Did I hear you correctly? Did you say your Fusion screen?
Yeah, I'm gonna do Fusion 360.
Oh, okay, cool. No, I was just wondering. It sounded like you had two screens.
No. You know where I stand on that, my friend. Okay, so let's go ahead and share the screen now.
So yes, we have friends from Italy that just joined us as well.
Nice.
Thank you for being here, Ice Cream.
Okay, excellent. So right here, we have a design that I've used before, and I've kind of modified it to add in a USB connector. You'll see it here on the board. This is a mini USB connector. I know everybody's moved on to micro, but this was the first one I found, so I decided to go with it. Okay, mini USB connector. So now if we look over here in the schematic, we have the connections to the USB connector. Now, if you look at one of those references that I sent or that I mentioned, and hopefully I can bring it up, but right now with the shared screen, here we go. Okay, you're going to notice that typically the differential pair that USB uses, they're named DP, DM. Okay, DP and DM, D plus, D minus. But in Fusion Electronics, you cannot use that naming convention, and here's why. In Fusion Electronics, in order to define a differential pair, you have to name the two nets in a special way. So you'll have a prefix and a suffix. The prefix has to be the same for both. So here I have D and D. The suffix, one of them gets underscore P for plus or positive. The other one gets underscore N for negative. There's no alternative here, so they have to be named this way in order for Fusion Electronics to recognize the nets as being a differential pair. Now, what other requirements do we have for USB, the USB differential pair? Now, in this case, I'm implementing a USB 2.0. So this is not the original USB standard, and it's not the one that's currently being used, which is USB 3.0. They're all backwards compatible, which is nice. But if you look at USB 2.0, you're going to notice there's some really strict requirements as far as making sure you have access to the maximum speed that USB 2.0 can do. So if we go to that data sheet, that app note, okay, you're going to notice that in order for the traces to work properly, you need to make sure that you have a twisted pair cable, which that's how the USB cable is made, so that part's okay. But you need to have a differential impedance of 90 ohms plus or minus 15%, and then each one individually 45 ohms plus or minus 10%. Okay? So remember how we were talking that in high speed, you need to be aware of impedance, and you need to make sure that you minimize any changes in impedance. Now, if you notice, the USB standard is fairly generous. So it gives you characteristic impedance needs to be 90 ohms plus or minus 15%. And then the single-ended impedance, so the impedance of each line on its own, is half that plus or minus 10%. Okay, now how do we calculate this? How do we figure out what we need to do to get that impedance? So let's go back to Fusion. And the first thing we're going to do on the board is we're going to make this a 4-layer board. Now, if you notice, I have the rest of the board routed. Like we were talking about earlier, it's best if you can make sure these are done first. But because of the location of this connector, it's going to work out fine. Now, one thing and another thing that we mentioned was keep traces as short as possible. The location of this USB connector has been chosen rather strategically to make sure I can keep this very close. Okay, how close does it need to be? That same document we were looking at specifies that for USB, you want to keep the connection from the connector to the chip less than 4 inches. Okay, so 4 inches is the maximum play you have under normal circumstances. If you needed it to be longer, then you would have to do some very serious engineering or some very serious trial and error in order to be able to get it to work. Okay, now how are we going to do this? First off, as we mentioned, because this is a high-speed signal and the nature of USB, one thing they recommend is to use a 4-layer board. That way you can have a dedicated ground plane and a dedicated voltage plane. So what we're going to do is we're going to go ahead and go into the DRC. And we're going to change it from a 2-layer board to a 4-layer board. Okay. Now you notice this thickness here is very big, 1.5 millimeters. Now, what you would do in this case to make sure you can calculate the impedance correctly is you would specify this to be whatever the impedance you needed it to be. What I'm going to do is I'm just going to use a value of 0.2 millimeters. And I'll just swap these out so we maintain the same stack up. The real information will be provided to you by the board manufacturer, so you'll have to talk to them, ask them what the thickness of the separation is here. That way you can enter that into the calculator to calculate your impedance. Okay, but we're going to use this value of 0.2. Okay, so now we have this thickness, we have 0.2. I'll say apply, cancel, so now it's in. Now what I can do is I can set dimension, I can click on the outline, and I can say convert to polygon. And I'm going to copy it to layer 2. Okay, I'm going to copy to layer 2. Now on layer 2, I want to go ahead and make sure I can select this. So I'm going to switch to design. I'm going to click the select command. I'm going to click over here. And I want to make sure that I'm on route 2, which I am. I want to use a width that's not 0. You can really use anything as long as it's not 0. I'm going to use 3 just to have something small. And I'm going to make sure this polygon is named ground. Okay. So I hit enter to ask if I want to connect it. I'll say yes. And now it's filled. And anything that's connected to ground gets connected with that trace. Okay. It's probably a little thin, so I can maybe change it to something thicker. I'll change it to 6, and there we go. Okay. So we have our ground plane. And what we've done, okay, oh, force a habit. We have an icon. Oh, wrong one, wrong one. I want this one. There. Okay, good. So we have our layer 2, that's a full, nice, intact ground plane. We have layer 1, which was going to route our trace. Okay. So now let's figure out what parameters we need to meet in order to have that 90 ohm differential impedance and the 45 single-ended impedance. Okay, and the way we're going to do that is there's a really nice tool called the Saturn PCB Toolkit. If this is a type of work that you're going to be doing a lot, I highly recommend downloading it. It is a free tool. Okay, Saturn PCB Toolkit. And this is really nice because it's basically a PCB calculator. It covers all of the different things that you would want to know about a PCB or that you would want to calculate. So if we look here, I've set it to the differential pairs tab. There are many, many different types of tabs here. Okay, with different things that you can calculate via capacitance. You can get very, very involved. Okay. But for our purposes, we're just going to use the differential pair calculator. So we're going to work with that.
Extremely useful calculator. I can't stress that enough, as Jorge just did.
Yeah, there's a lot to play with here.
There's a lot of information here.
So what we're going to do is we're going to set our target impedance, our target differential impedance, to be 90. Okay. Now we have this conductor width, this conductor spacing, conductor height. Now if you look here, we know from that 0.2 millimeters that this thickness is 0.2 millimeters. So we need to switch it to mils. I believe I can change the units here as well to metric. So I'll go ahead and do that for now, just 0.2 millimeters. Okay, I'll switch it back to imperial. It's about 8 mils. Okay. And we can see we're still out of range. We still don't have the impedance we need here. So what we can do is we can start playing with these numbers. Now, I've done it before. So I'm going to go ahead and enter the values that I got before, and you'll see that this gets us really, really close. Okay. Now, if you notice, this has a little color box here that once you're within the tolerance, as you can see here, then it'll go green. So 90 plus or minus 15%, 84 is within that. As you can see here, we're good. Then we have the differential, the single-ended one at 47 ohms, more or less. We needed 45, so it's also within the plus minus 10%. So this is going to be our conductor width, and this is the conductor spacing we need for a differential pair. Okay, and we obtain that by just playing with the values until we get what we want. So now, let's go ahead and set up the net class to be able to do this. So what we're going to do is we're going to go to the rules DRC. We have a class. Okay, I'm going to add a new one. I'm going to call it USB. You can call it whatever you want. This is a totally arbitrary name. Okay, USB. I'm going to make sure to put in the DN and the D underscore N, D underscore P. Select them both. Move them over. So now they're part of this class. And now we're going to go to the rules. So now if you see here in the rules, I have a default width here, which I've kind of broken here a cardinal rule in Fusion Electronics and in Eagle, which is you leave default alone. Okay. That way DRC can take over. In our case, we have 13 mils as our minimum width, so I'll pick 13. And then clearance will be 13. Okay. And actually clearance to itself will be 13. Okay. So at this point, we've set up a net class. And what we need to do now is assign these two signals to the net class. How do we do that? Click the select command. We click on the air wire. Let me actually reset the selection filter, otherwise I won't be able to select it. It's got the air wire. Net class 1 USB. It already is, right? Because I did it in the class dialog. And over here, 1 USB. By the way, you can always change it here as well. In older versions of Eagle, you had to use, you had to do it through here, but now the net class dialog can do it. Now you'll notice here that we have a tightness limitation. Okay. So there's a clearance issue over here. So what I'm going to have to do is I'm going to have to relax the clearance requirement a little bit. So let's go over here. Rules DRC, let's check the rules. If I set it to 12, oh, almost. 12, okay. There can be a little bit of back and forth with these things. Okay, so 11, it was good. Let's see how that affects our calculation. So if instead of 13, I have 11, we're still good. With 11, we're still good. Okay. So we are still good here. So you'll see there can be a little bit of back and forth here. And if it's not, then you have to make some other adjustments. But this is okay. 13 and 11. So we'll go back to Fusion. Okay, let me make sure they're good. Correct, that's what I want. All right, good. Say okay. So now we can route. Now, obviously, like I mentioned, you need to make sure the length is less than 4 inches. Now, another thing that's important to note, and it'll show up, and it shows up in that guidelines document, is that the max length difference that I'm allowed to have, in other words, the length of D underscore N versus the length of D underscore P can only be different by 2 mils. So they basically need to be exactly alike. Because we've created a situation where there's a good amount of room, and the routing is going to be identical. We're not going to have any asymmetries here. Okay, because if we did, then we would maybe have to try to meander, and that's going to introduce some asymmetry as well. So we want to avoid that. So by setting everything up nice, making sure we have a nice clear path to route, we're giving ourselves the best possible chance of having this connection be perfect. Now, how do we know, because actually I didn't address that earlier, how do we know that USB 2.0 is a high-speed signal? For that, I'm going to take you here to the data sheet. If you look, I believe it's over here. Here, okay. If you notice, high-speed USB 2.0 is at 240 megahertz. So if you want to use USB 2.0 high speed, remember our rule of thumb. If it's 100 megahertz or greater, it's a high-speed signal. Here we have 240. So we have to take this into account, and we have to be as careful as we're being, calculating our impedances, making sure the clearances are right. All of that becomes vital because of USB high speed mode. If we were just going to use full speed, 6 megahertz wouldn't be a problem. Low speed, 750 kilohertz wouldn't be a problem. But high speed requires it. And if we're talking about USB 3.0, which it runs, I think, at 5 gigahertz now, you definitely have to worry about it. Okay? So you can see here our rule of thumb is validated because of the speed that USB 2.0 can go at.
5 gigahertz, that's pretty respectable up there.
Oh yeah, big time. So let's go ahead and let's route this. So we're going to use the design. You'll notice we have different route options. We're going to do route differential pair. Okay, when we do this, you'll see it sees it. I can select it, and you see it wants to keep them together. It's going to respect those clearances that we were talking about. We want to keep symmetry. We want to keep them identical. Okay. Now, as we get close, you have two options. You can either escape and then route each one individually using the single route, or you can hit enter and try to let the Fusion Quick Router finish them automatically. That's what we're going to do in this case. Hit enter, and they route automatically. Okay. So you can see they keep that minimum clearance as they go through of 11 mils. Now, how long are they? Because that is important to us. Now, what we can do is we can use several tools. One of them is over here. We can go to signals. We can search for,
I think it's D, the name of the signal, D.
Mm-hmm. The thing is, it's not showing all the net classes now. Wonder why it's doing that. All right, we created a new one.
Did you save?
Ah, that's what it is. Thanks, Ed.
Hey, man, any day.
So I'm going to go ahead and save from here.
So if you kind of knew the Fusion, this is called the electronic document. If you knew the Fusion, this is what we call the electronic document. It kind of keeps your schematic and your board linked together. If you're an Eagle user, as you know, you put your board and your schematic in one folder. As long as they have the same name with the appropriate prefix, they will be synchronized. When it comes to Fusion 360, you actually create an electronic document. And from that electronic document, you create or load a schematic and a board, and that's how it keeps them linked.
Yeah, it doesn't like to show them here.
Go ahead and type class and make sure that you actually did define it, all right?
Yeah, it's there. Should show up here too. No worries. We'll use a filter.
There you go. We always have options.
Mm-hmm. So when I say object type, it's going to be a wire whose name equals D. There we are. So you have DP, DN. I can sort. What I can do is I can select the whole trace. And when you do that over here, you can get the length of the individual segments, I believe. And you can add them up and it'll tell you. So that's one way.
So just to let you know, the design manager filter, we covered that topic. I think it was last week. No, it was 2 weeks ago. So just in case you want to learn more about using the design manager and the filter, how to be able to find assets within your design, it's actually very useful. So as you see here, Jorge used to find a filter. That way you could easily find all the traces that belong to a particular signal.
Correct. So if we look here, we know that 4 inches is 4,000 mils, and the sum of all this is less than 4,000. We don't have anything here that we could think we would be in trouble. Okay, so at a glance, I know it's less than 4,000 here. So I will apply this again. Let's check the P's. Okay, same thing. Yeah, nothing concerning here. At a glance, you know it's less than 4,000.
Hey, Jorge, I don't know if you want to try it. I mean, we're here already. I don't know if you want to click on automate, click on ULP and run that ULP called length.
Yep, that one we'll do it as well. Oh no. I changed the I changed this entire thing. Let me fix it. One thing to be aware of, if you hit your scroll wheel while you're here, you'll notice that it'll change the sizing. Okay? And it'll do the same thing with the style.
Yeah, yeah. The wheel will cycle through the options.
And I'm used to doing that to like move the screen up and down, so I have kind of that bad habit, and I ended up totally mangling the trace. Okay, so we're good there. So now, as Ed mentioned, we can use that ULP. So we'll go ahead to automate, select ULP, and you can search length. Say length, hit enter. And I can actually, I could do this as well and just type them in. But if I run it as is, it tells me nothing. I thought this one brought up a table.
No, just go ahead and click OK. It will bring it up.
Oh, there it is. Okay.
Yeah, it'll bring it up. It'll bring it up. It just gives you some instructions there in the beginning.
So let's see.
There you have DN and D underscore N and D underscore P.
In millimeters. So I got to convert.
Yeah. So yeah, it's just to let you know that ULP stands for User Language Programming. It's a way by which in electronic editors we can expand its capabilities. It's a C-like language, and we just had one that was made. I don't remember who made it, but gives you a list. You could use it to create custom custom exports or custom imports. And in this case, this ULP just creates a report of all the lines and gives you all the measurements in millimeters. And now that you mention it, maybe we should make a change on it. That way we could also have it give us the option for imperial.
Yeah, and even then, though, if you look at it, it's making some mistake because it says there's a 1 millimeter difference here between DN and DP, which there can't be because they are identical.
Okay, gotcha.
So they are running together. I mean, technically, one on the insides may be a little bit shorter, maybe, but if you look at the center line, it should be equivalent.
It looks pretty spot on, yeah.
So But that's basically what you do. Here we've made sure that they are symmetrical, that they stay together. And in doing so, we've done everything that we can do to make sure that this USB connection will be successful. Okay. So key takeaways, rule of thumb, if you have something that's 100 megahertz or higher, you need to be thinking about, okay, this is a high speed signal. I need to treat it with care. If you're doing a USB application like we did here today, then you'll probably have to calculate what widths and separations you need in order to achieve the differential and the single-ended impedance that's needed for the USB standard. USB isn't the only game in town. There are other protocols that also specify the impedances you need to use. So this is something that you probably would be doing in other protocols as well. Okay, so Ed, do we have any questions? I got to
Thank
believe
you,
we got
Jorge.
some questions.
Appreciate that. No, the only question that we had on Hein right now was the fact of getting a report for all the length. So you went, you and used the ULP, which is basically what I was trying to get to. Also, just wanted to let you know that the Saturn PCB calculator, if I'm not mistaken, it seems that it's only available for Mac. I'm sorry, for PC. So there are some, if you do Google search, there are a few that are online. The nice thing of the Saturn PCB is that it's in one place, so you could access all of them. It's kind of neat. So
and here it was. Now the design manager shows it, but this is what I was trying to do.
yeah, there you go. There you go. So there you have the entire length. I guess it just took a while to save, and that way you could get it as part of it.
Yeah, maybe.
So as you could see, the design manager actually gives you the full length as well. It's just funny that just recently I had a case and they asked this question, and this is where I guided them to do it, as well as using the ULP as well. So if you have any questions in this regards of the topic that we covered today, please join us on the Fusion 360 Electronics Forum. I'll go ahead and put a link for it. If you give me 1 minute here. We do have a link for it. I created it.
Looking at it, it's still, this one still wouldn't comply because it's 39 mils different when they should be just 2. So one option it would be to meander. Another one would be to try to make this connection completely straight, or in some way where I don't have this bend, because of making this bend, I lose length. So I could try using the meander command to equalize them a little bit just to show it real quick.
Yeah, so the meandering is basically, I don't know if I should use this vocabulary, but it kind of adds zigzags.
Basically,
It creates these zigzags in an attempt to give the exact length between both traces. As you could see there, that little hump.
Okay, what we want to do is in the DRC, you can specify what the tolerance is, and you can also specify the gap factor. I never liked the gap factor being that big. I don't know why we default with that one.
Yeah, I know that you've always recommended to change it when we've done these presentations before.
But oh well. So this would be 0.05 millimeters is actually what it would be.
That's the, okay, yeah.
That's the
Remember,
2
you
mil
calculate,
tolerance.
that's what you calculated, yeah.
So if I cancel, let's try to make them even. Let's see what happens. It's going to be a little tight. And we really want to try to avoid, having to have this asymmetry, because that's what this is going to be. This is going to be an asymmetry right here.
That's why you want to try to do this in the beginning before you have anything else in your way. That's why you want to do this type of routing before you actually do anything else on your board. So if you have differential pairs or anything in the category of high speed, you want to just take care of those first.
Okay. Any questions, Ed? We got anything else?
No, I think we're good.
Excellent.
I have somebody here, but I think you covered this already. It says, how do you calculate this difference in lengths?
So the easiest way is here in the design manager. This is literally the simplest way. But but it wasn't showing up earlier. So we had to go with using a filter and selecting the traces and trying to do a little bit of math, or the UOP, which now probably is going to be proven to have been true. So actually, I'll just do run length d underscore p d underscore n, and it's been proven to be true. It wasn't wrong. It was correct before.
Okay, so it's spot on now. So it did work then.
It did work. Yeah.
Okay, very well. So somebody that participating in our forum on our live stream is asking, so why did you use 0.05 millimeters?
So the 0.05 millimeters comes from here in the DPDM requirements, if I'm right.
This is on the manufacturer's specification sheet.
Right. Over here
for USB 2.
Says no more than 4 inches. Noise rejection parallel to each other within 2 mils in length of each other. 2 mils in length. So 0.2 millimeters is 8 mils. So 2 mils would be that divided by 4. 0.2 divided by 4 gives you 0.05. That's why I use that.
There you go. Well, thank you, Jorge. We really appreciate the topic. As always, phenomenal work for the introduction to high-speed designs and how to actually, part of it I'm getting out of this is the actual what to look for on a specification sheet. What is the information I need to extract? That way I could understand, how am I going to apply that on my design? I thought that was a really good introduction, the way you put that together. And takeaways, well, as he said already, the threshold is around 100 megahertz, I think he said.
Yep.
So that's your threshold. Anything above 100, then you got to really take a look at the spec sheet and be very careful with your, take those routes into consideration first. And we have tools there. We have the meandering, and we also have differential pair routing as well. And I'm really glad that you used this example, because when it comes to USB, I think everything has USB now. It's just
It
the most
does.
common interface. It's hard to find a device that does not have a USB plug on it, either micro or the regular USB. So kind of glad that you use this example, because it's one of the examples I've used on a different design as well. Thank you, everybody, for joining us. We had people from around the world to join us. It was great for you to be here. Next week, Jorge and I and one of a member of the developing team, we're going to be talking about the latest implementations in Fusion 360 electronics. So we're going to actually cover everything that has released since January, when Fusion 360 electronics actually was implemented. We're going to cover all the new tools that are available and how and when to use them as well. So we'll cover quite a bit. I think we're going to spend a lot of time, Jorge, mainly on the libraries. I think that's where we're going to be spending quite a bit of time, because that's where the most kind of like noticeable improvements have been done. So hope to see you there. Thank you, everybody, and have a great day. And remember, stay safe. Thank you,
Bye,
Jorge.
everyone.
Thanks. Bye now.